took a short break. Went out, had 3 beers. I'm ready to go. Whew. It's only been a minute, so I'm just kidding. I'm a kidder. Okay, I'm kidding. I wouldn't kid you. You're not a goat. I wouldn't kid you. You're not. Okay, back to the problems. Okay, now third problem on here says. Here we're going to have a buffer solution, and now we're going to throw some either acid or base I didn't look at into it and see how the buffer deals with it. Okay, so here's a question. Calculate the pH of 1 liter of the buffer, 1 molar sodium acetate and 1 molar acetic acid. Same from the last problem, okay? It's the same buffer system from the last problem. I did that so we can kind of do the math a little quicker. Before and after the addition of 0.080 moles of NaOH. So, before the addition of anything. So just having the buffer system. In this case, it's 1 molar and 1 molar. We know the answer to that pH. We know what it is. We just figured it out. Now, I was showing you before that when we have that system, the concentration doesn't change the pH of the buffer. Okay, so it's going to be the same pH, which is 4.74. You can do the math again if you don't believe me, but those ones from the concentrations will cancel out. And we get the same X value, 1.8 times 10 negative fifth, and it'd be a pH of 4.74. So the pH of the solution is 4.74 before we add anything. But then we add something to it. Okay, this is where we're going to start doing some fun stuff. Let's go ahead and re-put up the equation. All right. There's our weak acid. We've added some salt to it to spice it up with some acetate ion in the solution as well. This time we had a 1 molar solution, if I do recall. 1 molar. So we start out initially with this. So we start out with 1. But what I'm going to do is actually I'm going to make a little room here because we know that's what the setup of the buffer is. We did that in the last problem, so we know what's the setup. But this time, we are going to add some sodium hydroxide. Okay, we're going to add it in, so let's throw that in. Let's put that into the solution. So CH3, COOH, plus we added sodium hydroxide. So NaOH. Now remember, with the buffers, I already explained, if we add hydrogens, the hydrogens will be grabbed by the acetate and we'll get rid of them by throwing this to the left. If it's hydroxide, it's sodium hydroxide, that we all remember is a strong base. So we add that in, that's going to have to be chewed up by the acid, neutralized, all right? So we'll neutralize that, and now it's going to create some acetate ion and throw the reaction to this direction. So add hydrogens, throw it this way, add hydroxide, you want to throw it this way. So what do we have for starters? Okay, so for starters, we have, how much sodium hydroxide do we add? 0.080 moles of it. So 0.08 of it. That's kind of small on that screen. Now we'll make it a little bigger. All right, 0.08. We start out with 1 of this. Okay, we have 1 of this. All right, so we're kind of hanging around here. So this is kind of going back and forth. We don't have any of this to start. So here's what we had. We had a nice, happy, nice equilibrium system. And then what do? You decide to dump in this base. Deal with that buffer. What you got now? Buffer goes, here's what I got. Okay, now, so you put this into solution. This breaks apart. You get 0.08 hydroxide. The acid goes, my turn. It's going to release some of these hydrogens, and that's what it's doing anyways. It's pumping out hydrogens here. Not many, but it's weak, but it does. And those hydrogens that it puts out will neutralize the hydroxides that were put in by that strong base. Neutralize you. That's what I'm going to do. Neutralize you. And the sodium hydroxide goes, melting, melting. So we will get rid of this. For every OH we have here, we will combine it with an H, and we will deal with you. We will get rid of it. Now, there's a cost. There's a cost here. We're going to lose some of the acid. Because we're losing the acid, because we're losing hydrogens, which means we're losing the acid. Remember, that's what the acid is here, it's hydrogens. We're losing these, which means we're losing 0.008 of my weak acetic acid. We're losing that to neutralize this, so we end up with none of this. We can get rid of it. But I'm going to lose 0.08 of this in order to deal with you. Done. 0.08 of the hydrogens came off to neutralize the OH. That means that I now have an extra 0.08 acetate that I've created that's floating around. Remember I said we're going to take this and push it to the right, and we push it to the right by creating more acetate ion. So we picked up 0.08 of that. All right, so we've lost 0.08 of this to deal with this and neutralize the hydroxide, but that creates an additional 0.08 of the acetate because the hydrogen is now gone and it's now just acetate. So what that means is we've neutralized this, lost some of this, gained some of this. Now at this point we're not at equilibrium anymore. We were before we added the hydroxide. We were at equilibrium. They were just kind of hanging out. Kind of like the 60s, man. At Woodstock, everybody grooving and having a good time. Then all of a sudden, you throw this stuff in, and we dealt with it. But now this side's going, wow, I've changed. And this side's going, me too. And we've got to reestablish an equilibrium. When we reestablish our equilibrium, okay, here's what we're going to have to start that off. We now have initially 1 minus 0.08 or 0.92 of the acetic acid left because we lost some of it to neutralize that base. Now we've gained some acetate. 1.08 is now what I have. We have 1, and now we have 0.08 added. We have 1.08. So notice this is my I. This level here is not the initial in my ice chart. That's the chemistry that's happening. The initial in my ice chart now, to make my equilibrium ice chart, starts out with 0.92 of this. None of this, we got rid of it, so this is gone. 1.08 of this, and 0 extra of that floating around because we used it actually all to chew up this. Okay, we've used all the H's. So at this point, upon the neutralization of the base, we don't have any hydrogen. Okay, let's go through, now do the ice chart, do the equilibrium setup, equilibrium Ka, products of reactants, get a value for this, and see where we are with our pH. Okay, change, negative X, positive X, positive X. I like putting the line, so 0.92 minus X, 1.08 plus X, X. The K of acetic acid is 1.8 times 10 to the negative 5. That's equal to 1.08 plus X times X divided by 0.92 minus X. Yes, those X's do go away. Again, if you don't trust me, do your rule of 100 and you'll see they go bye-bye. So we're going to get rid of those. Now, in the earlier calculations with this system, those canceled out because they are equal, but they're not equal, so I can't cancel them out. So I am going to have to do the math here and see what we get. Come on, turn on. All right, so 1.08 divided by 0.92. That's what I'm going to do here. 1.08 divided by 0.92, okay, is 1.174. So this is now 1.174x, and then divide by 1.174. That'll give me x. That'll give me my hydrogen. And I'll put that into my pH equation, but let's get a number for that. So 1.8 second function exponent -5 divided by 1.174, and we come out with 1.53 times 10 to the -5th, 1.53 times 10 to the -5th. That's my hydrogen. Put that in your pH equation. So pH is equal to -log of that. And so let's see what we get. All right. Let's see. Log. Kids love logs. Ren and Snippy. You probably don't remember it. What was I doing? Went off track. Oh, fine. Yeah, pH. So the pH on log. Where's my log button? Log. Come on, log. Where are you? There it is. Okay. So log. Second function answer. Bam. 4.81. 4.81. Now, maybe you can get what I did. Maybe you were able to follow it. Maybe you weren't. If you weren't, go back and watch this again. Go through it, digest it slowly. Okay, don't digest too fast. You'll get indigestion. Go through it. You can get this answer, great. But what does it mean? I always been trying to tell you, I want you to understand something, try to make some connections. We just added a bunch of base to our buffer solution. What's the buffer solution supposed to do? Keep the pH relatively stable. That doesn't mean identical. It means in the ballpark. It can be close to what it was. Now, we started out with this solution of a pH of 4.74. We dumped some base in there. The buffer went to town. All right, did its job. Took care of that invader. Dealt with it, neutralized it, gone. And we ended up, after that, with a pH of 4.81. 4.74 to 4.81. It's pretty good. It kept the pH pretty close to what it was. And it dealt with the hydroxides. Now, we did add hydroxide, so that would make sense that it did pull up the pH up, hydroxide up a little bit. So that answer makes sense. The buffer did its job. It changed a little bit, but that's okay. Those are the buffers supposed to deal with it. You know, the buffer's like, you go, buffer, look at you, you've been in a fight. Yeah, you should have seen the other guy. I look good. Okay, all right. So now we solved that problem.